Hello. So today we're going to be looking at the dot product calculations. And in this example, I've got a sphere here with a bunch of points scattered on it. And we are going to work out how to only scatter points on those faces that have a Z component to their normal. Okay, let's dive into it. Let's quickly look at how the dot product works. This arrow is pointing directly up on our y-axis, which means it has 0 on the x and 1 on the y. And this angle is pointing directly on the x and nothing on the y. Now, the dot product lets us test the difference between these two vectors, and it will output what's known as a scalar, which is just a single value. In this case, when a vector points 90 degrees away from the opposite, the scalar would be a value of 0. If, however, our vectors are both pointing in the same direction, so if they were both like this, pointing upward, 0, 1, we would get a value of 1. And if both vectors were pointing in opposite directions, so one was pointing up and one was pointing directly down, so 0, minus 1, we would actually get a minus 1. So what dot product lets us see is if we have an object and we want to know which faces are pointing up, for example, in the y-axis, we can then just get the normals and test them against a vector using dot product. And if we get a value of 1, we know that they're facing in the same direction. And any value slightly below 1 will tell us how much they are pointing away from our vector. So that's a very useful value to be able to scatter points, or in a game be able to know if your enemy is running in the same direction as you. So let's try and visualize this quickly. I've got a single point here at the 0, 0, 0. So it's just sitting at the origin. And we want to test two vectors. So I'm going to create two vector nodes. And for this example, I'm going to test x and y. So let's test looking for x1 against y1. So in our previous example, that would have resulted in a dot product of 0. So let's create a vector math node, set it to dot product, and connect those two vectors. Now, to visualize this scalar value, which is a gray node, I need to plug it into our position here. So I'm going to plug it into our Z position. So as this dot product evaluates, it will move this either up or down. So let's drop in a combine XYZ. And I'm just going to plug that single value into the Z. So it's always going to be 0, 0. And I'm going to plug that into our position. Meaning that as we evaluate any amount of X value on our vector, it will get closer to the value of 1 here, meaning our dot product would start to evaluate towards 1. So any value of X means it will be starting to face towards that direction. So as I increase this to 0.1, you'll notice that our dot product value in the Z has started to increase to 0.1, 0.2, 0.3, 0.4, and you can see that is moving up on the Z axis. So by the time I get to 1 here, we are now facing up on our x-axis and up on our x-axis, and therefore our dot product equals 1. If I set our x-axis here to -1, we should get a minus value, meaning our vector is pointing 180 degrees away, and so in the opposite direction. So this is a good way to just visually show us here what that vector is doing. It's not showing us where the vectors are pointing necessarily, but it's showing us the value of are they pointing towards each other or not in the same direction. I just want to quickly point out that when we have a vector pointing upward like this of x0, y1, and we are testing against a vector like this of 1, 1, that would be going right to that point. Basically, dot product measures how much of the first vector is in the same direction as the second vector. It's quite a more complicated calculation we would need to make to accurately measure the difference between these two vectors, taking their magnitudes into account, but I think I'll cover that in a separate video. So let's take our example a little bit further and actually show this in a much more interesting way. So back to a new scene, jumping over to geometry node, and I'm going to create a sphere. So this has a load of points on it. We can zoom in on that, as you can see. And all of these polygons are facing in a specific direction in 3D space. And we call those the normals. So that normal is facing out from there. This one might be facing up a little bit from there. These ones are facing down. And we can test that in geometry nodes by simply dropping down a normal node. So the normal node now gets all of the normals from this object, and it is purple, therefore it's a vector. So we can now test against that vector. So let's drop in a vector node that we want to test against, and let's test on the z-axis, the facing up axis. So again, let's create ourselves a vector math node and drop in a dot product and connect that to there, connect that to there. We're going to leave this for now. Now that dot product value is obviously going to be a scalar value for every one of the faces on that sphere. And I want to do a simple check now, that is a math check. And I just want to know the values that are greater than a certain value. So anything greater than 0 would be any normal, any polygon face that is facing vertically. So let's drop down a distribute points, search distribute points on faces. I'm going to plug my sphere into the mesh. And if I just plug this straight into there, we'll get points all around that sphere. But now let's plug the value of this into our selection. And you'll see now we are only getting points on the top hemisphere. And that is because we are greater than 0. We are looking at only the faces that have a z component to their vector. If I change our threshold, however, on the greater than, we can start to clip this amount here. So if I say only show me the points at point 1, you'll see now the face needs a z component greater than 0.1 to the vertical normal or the vertical axes. And if I can increase that a little bit more and a little bit more, 0.5 is showing us roughly the top quarter. And if I keep going, eventually it will only show us points that face directly upward, which there are none because they all have a slight downward angle. So this is a very useful way to create a system that might scatter points that are looking into a specific direction. Like here we are only looking at anything that faces upwards on that sphere. And I can just drop in a join geometry node here. And if I plug our original sphere in and our points in, and I plug that into there, you'll see them on that sphere. So you can see if I jump over to our side view here, none of those faces here point directly upward. They all have a slight angle to them. And that's why when I set this value to 1, we have no points. And then I get some on these faces. These are all below or between 0.9 and 1 and so forth. So that's a very useful use of the dot product in 3D.